When using laboratory equipment, we must read instruments using correct precision. We cannot estimate values that are not measurable on calibrated lab equipment. So if the laboratory equipment can only be measured to the 10th place, we cannot estimate value in the 1000th or the 10,000th place. The general rules for estimation is, for digital scales, they are already to precision. Just write down all the values. Other equipment, you must find the smallest calibration mark and add one extra digit. This first example is a triple beam balance. Since this is not a digital scale, we must read it to the correct precision. So read the scale like you normally would do. So we have a 90, 400, and 8. It's close to 9, but not 9, so it is 8. So if we add all that up, 400 plus 90 plus 8, we know the triple beam is approximately 498. Next, look for your smallest calibration. Our smallest calibration is located right here. These are our smallest calibration. From 5 to 6, we know this is 0.1. Next increment is 0.2. The next increment is 0.3. So all the smallest calibration are in increments of 0.1. This tells us that the increments for the smallest calibration is by 0.1. So if I expand this out, and this is 0.1, we know the next hash mark is 0.2. We can estimate between 0.1 and 0.2. So if I have my mark at this point, this would be 0.15. So if you notice, we were able to estimate one extra position. For this triple beam balance, we could estimate to the 100th place. When I read this scale, this will be 498.9, because this right here is 0.9 right here. And we must estimate one extra place. It could be an 8, it could be a 9, and they would both be correct in grams. So you need to find the smallest increment and add one more digit after. So in this case, the smallest increments went by 0.1s, or it was in the 10th place. I add one extra digit after. And in this case, it was an 8. This is an example of a graduated cylinder. If I read this, this is above a 10. Each of these hash marks are by ones. This is 10, this is 11, this is 12, 13, 14, 15, all the way up to 20. The water is approximately 12 milliliters. If I expand the section between 11 and 12, I can estimate an extra position. Because if I had a mark at this point, this would be 11.5. This might be 11.6, and so forth. So our lowest increments, we said, went by ones, because this was 11, this was 12, this was 13, so it increases by 1. So it was in the ones place. We estimate one extra digit after. So this is going to be 0 mLs, 12.0 mLs. Let's look at this example. Again, we're going to read the scale as is. So this is 2. We know these little hash marks are by 0.1s. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So if I just read it, I know my estimation is 2.6. If I expand my mark at 0.6 to 0.7, I could estimate this middle section to the hundredths place. The correct answer for here is 2.65 ml. So the smaller increments went by ones, so that is the 10th place. After we determine the smallest increment, we add an extra digit. So we needed a digit at the hundredth. So in this case, it was a 5 in the hundredth place. Read the graduated cylinder. It is approximately 28 milliliters. Find the smallest calibration mark. The smaller calibration mark increments are by 1. This is 28. This is 29. So that means we can estimate between 28 and 29. We can estimate an extra digit between 28 and 29. Each of the calibration marks are in the ones place. To estimate one extra digit, it must be located in the 10th place. So the correct measurement for this graduated cylinder is approximately 28.2 or 3 milliliters. The 28 is the smallest calibration mark location, which is the ones, and the 2 is the estimated digit after in the 10th place. Estimate the height of the paper clip. The paper clip is approximately 2.6 centimeters. The smallest calibration mark goes by 0.2. So the first one is 0.2, 0.4, 0.6, 0.8, and then 3. Between 0.2 and 0.4, we can estimate an extra digit. So the smallest increment is in the 10th place. We could estimate an extra position or digit in the 100th place. So the 0.6 represents the smallest calibration mark. The estimated digit is approximately 0.8. It could be 0.9, 0.7 centimeters. If this was in millimeters, it would be 26.8 millimeters. For each of the upcoming examples, pause the video, try the example on your own, and then check your answer. For this particular graduated cylinder, we're going to approximate the measurement as 3.4 milliliters. Now determine the increments of the smallest calibration mark. The calibration marks go by 0.2. This is 0.2, 0.4, 0.6, 0.8. So if I expand 0.2 and 0.4, I could estimate an extra digit between the two. Since the last calibration mark is in the 10th place, I could estimate an extra digit in the 100th place. So here is our calibration, our smallest increments provided by our calibration mark, and our estimated digit is going to either be a 5, a 4, or a 6. Correct units of milliliters. Find the smallest increment and then add an extra digit. Here's a triple beam balance. It is 500. The next beam is 40. The last beam is 5. So we know that the triple beam balance is approximately 545. We find the smallest calibration mark or increment, which is right here. These are all divided into 0.1 intervals. So this is 0.1, this is 0.2, this is 0.3. So the smallest interval is in the 10th place. We could estimate one extra digit, so our estimated digit must be in the 100th place. So that's our calibration mark, smallest calibration mark. Here's our estimated digit in the 100th place. So our correct measurement is 5.2. This is our calibrated mark, and our estimated mark is 0 or 1 units of grams. So this triple beam balance, the first beam is 10. The second beam is 400. The third beam is between 2 and 3, so it's going to be 2. So if I add that up, it's 412. The smallest increment, which are these marks right here, and they go by 0.1. This is 0.1, 0.2, 0.3, 0.4, 0.5. So between 0.1 and 0.2, we could estimate an extra digit. So we must write our precision to the 100th place. So here's our calibrated mark, which is the 10th, and our estimated mark, which is the extra digit, and that is in the 100th. So the real measurement for this triple beam balance is 412.50 or 1 or 49 is another one, grams. The first measurement is 300. The second beam is 50. The third beam is 4. If I add that up, this is 354 approximately. So we find the smallest increments. The smallest increments go by 0.1. So this is our calibration mark. We estimate one extra digit, which is in the 100th place. This becomes 4.60 grams. For the ruler here, it's in centimeters. It's approximately 6. The smallest increments go by ones. This is our calibration mark, our ones. So we estimate. So after ones, it becomes the 10th place. The 10th place become our estimated mark. So this is approximately 6.7 centimeters. We find the intervals for the smallest calibration mark and add one extra digit. So the calibration mark was by ones. So we add in an extra digit, 0.0. For the thermometer A, it is approximately 21. The increments are by 1 because this is 21 and this is 22. So that means I could estimate between 21 and 22. The smallest calibrations are by 1. This is the ones place. So that means we could estimate one extra digit in the 10th place. So the correct answer for this is approximately 21.7 degrees Celsius. The bottom one is approximately 21 degrees Celsius. The smallest increments here go by 0.1. So this is 0.1, 0.2, 0.3, 0.4, 0.5. Since the smallest calibration is in the 10th place, this is the 10th place, we must add an extra digit, which will be in the 100th place. So our estimated digit is in the 100th place because our smallest increment was in the 10th place. So this one, our answer would be 21.65 degrees Celsius. So if you notice between A and B, even though they are both thermometers between 21 and 22 degrees Celsius, B had better calibration. We were able to approximate an extra digit versus A. So again, find the smallest calibration mark, find the increments for that smallest calibration mark, and add an extra digit.